How you guys doing? Some awake, some not so much. All right. Last time we began talking about granular filtration, and today that's what we'll be dealing with. I appreciate the feedback you guys gave me. I read through, and it sounded like a lot of you were appreciating the example problems and perhaps wanting some more. So we'll try to incorporate some more. So thank you for that. Also appreciate the participation in that activity. I'll be posting some more, perhaps some on Moodle, some Kahoots as we go. So just be alert to that. I think I'll mention later today, but now's this topic here today is really a big part of what happened with the Milwaukee cryptosporidium outbreak back in 1993, is the granular filtration systems, turbidity monitoring, that kind of stuff. So do be taking a look at that paper if you haven't. It should be posted to our Moodle page, and there will be a quiz associated with it at some point soon. I'll put it live. Okay, so we left off last time kind of talking about what are some of the basic terminology that we'll use and a bit of the background on granular filtration in general. And really it's all about using sand particles or something like that to filter water, but not filter in the sense that we might think of with a membrane where it's physical separation, but more so you're going to catch the particles. It's going to be like getting them to just stick onto the wall as they pass by, and giving a lot of opportunity for that to happen. So it's more like an adsorption reaction in that sense. And the terms we're going to use is filter ripening. If you've ever had a brand new Brita filter or something where you're flushing your water through, first few minutes there's going to be these black specks coming out, and it looks messy. Well, that's because when it was made, there's just some smaller debris in there, and they haven't all been caught. Some of it's just loose and ready to flush out. And after operating for some time, you'll be in a more stable, settled sort of situation. More of you can participate with, but it's kind of neat. You can backwash it. It's just hooked up to the tap water, so we can flow it. We can watch some of the debris coming out if we backwash it. It's not particularly dirty, but it's kind of has all those new particles, or the small particles from being a new filtration media. Okay, so the other terms I want to cover are head loss. We typically load our filters by gravity. That's a little different in the case of the one I just showed. In these kind of containerized or these pressurized systems, you would add pressure just by pumping. So it's a watertight system. You pressurize it with some sort of pump, and you're pushing water through that way. Most of the time we operate with an open bed, and it's just gravity that's pushing water through. And as there becomes more resistance with more particles stuck around in there, you naturally need more gravity, more force to push the water through, because you have some more resistance there. And so you'll add water at the same rate. Let's say, I don't know, for a few filters, maybe 1 million gallons per day, constantly all day. But as they get clogged, the water level will rise, pushing more force through them. So it's a nice natural way to stabilize your equal flow rate. You have a continuous flow rate over time, because as your head loss raises, your water level is just going to raise with it to account for that. Okay, so that's what we're talking about when we say head loss. Turbidity, you should know by now what that is. A couple slides just to demonstrate again, but that's just simply the measure of the number of particles. It's not an exact measure. It's just how much light is scattering, and we have some correlation. So there's some units, nephelometric turbidity units, NTUs, and just again real quick, that's clear to very turbid water. So perhaps what you're treating in the drinking water plant might be this second one to get water that's as clear as the first one. So maybe this is the water you're treating so that you get something like this. And then when you backwash, it's going to look more like this, right? That kind of might be how you would expect it to happen. I think we talked about this. This is a little device to measure. You can kind of see how that works. Okay, so then the real question with granular filtration is how often do we have to backwash, and what does that mean for the number of filters we need, for the amount of volume we need to produce? How are these things tied together, and how can we understand the net amount of water we can produce given some number of filters? So the first thing to consider is, well, when do we need to backwash? Typically, this could be anywhere from every day to every 2 to 3 days, something like that, maybe even 4 days. We'll have some sort of a cycle. And the cycle will essentially consist of a few parts. First, this ripening. We give it time to clear out any of the bad particles that were there in the previous cycle we just backwashed. So we'll start by that ripening. That'll be kind of our cycle start. And then we will go on and do our filtration for some time, and then we'll backwash. And so when we think about this, some entire cycle, which I'll describe it in more detail in a minute, what we might want to monitor over this time during filtration. So if we just look at this part of the cycle where we are actively doing our filtration, we want to know at what point do we have to stop it to end our cycle, to do the backwash and all that. And so what we might monitor is perhaps the head loss. So we might monitor the pressure or the water height over time. And once it reaches a certain level, we say, okay, that's enough. We have to stop. So head loss might be one. Time limit, just simply, okay, after 24 hours, we always cut it. Maybe that's the most practical thing, and you just have a nice routine going. Or perhaps it would be a turbidity limit. And if you think about what this might look like, if we do give the turbidity a look when we do, let's say, a ripening stage and then filtration, and we simply monitor that, and we say we have some mandatory cutoff. So this is our limit. And let's say this is our turbidity. Well, if our limit's up there, during the ripening stage, we often have over the limit, which is why we're not going to use that water. So for those first few minutes of operation, we probably have a pretty high turbidity, and then it comes down and will look something like this. And so then once we breach that limit, that's when we say, all right, we would definitely stop the cycle right there. So this would be the turbidity limit here. Now, in practice, we usually have multiple of these limiting factors. We might say, all right, if it ever gets above a certain amount of hydraulic head required, then we are going to stop. If it ever goes beyond 72 hours, we're just going to go ahead and stop it and do a backwash. And we'll monitor the turbidity the whole time, which is normally a requirement. And anytime it goes above some certain threshold, we know we have to stop it and backwash. So typically you'll have at least two of these, at least turbidity and one of the others. We'll do a lot of problems in class with a time limit, just to say, all right, here's the cycle time. Let's calculate from there. But this is kind of in practice what you'd be considering is the pressure, the turbidity, or some time. Okay, so let's take a look at head loss then, and here I'll take a moment to really define our typical cycle. We'll have some early part where we are rinsing or ripening, That would be interchangeable. That would probably be something like 15 minutes. Then we have our filtration. This would typically be anywhere from 24 to 96 hours. 96 might be a lot, but. And then after that, we would have some sort of backwashing. And we might have a couple steps here. We might have maybe an air injection and then a regular backwash. Really, we could call both of those steps the backwash period, but the difference would be we're not using water during the air purge, so we're not sending that water to waste or consuming water that we've already produced. So that's why we might distinguish it. And in total, this would also be something like 15, 20 minutes. Okay, so we see here then that maybe half an hour of some total cycle is dedicated to this backwashing rinsing process. So something like that, probably less than an hour, and our total amount of time would be on the order of 24 plus hours. So it's a small fraction, but it is a fraction, and we're going to also consume clean water that we produced in order to do both the rinsing and the backwash. Okay, so then if we take a look at head loss over this type of a cycle scenario, as soon as we clean the filters, let's imagine a limit here. As soon as we clean them, water is going to flow more easily through them. So even in the rinsing phase here, we're going to have a pretty low head loss. So there's going to be some resistance, but it's not going to be too bad. And really, it's just going to be pretty much a linear line going up. And if I was drawing this perfectly, I would say we would, at this very moment, we would cross, and that's our backwash. You know, in the way I drew it here, this would be our cutoff, our limit. So at that point, then we would backwash. Does that make sense? Pretty straightforward. The reason I'm spending a fair bit of time on this is because when we calculate our overall filter efficiency and how much water do we actually have to add over time, we have to come back and think about the amount of water we consumed for rinsing and the water we consumed for the backwash. So I really want to make it clear these steps so that we can orient ourselves when we take a look at the equations. All right, so let's pause a moment and take a look at what it looks like in reality. So I'm just going to play a YouTube video I found on this for you here. Might turn off the lights. So just give me a moment. Might have to adjust the sound, so bear with me. Okay. So there's some people taking a tour in this water treatment plant, and they're just starting the air purge here. And this is water. What we're looking at is water that's on top of a filter bed. I'm going to turn off the lights for a moment. So you can see it looks pretty gross, and then they would do this probably for the next 5 minutes. So we will skip ahead a little bit, maybe just a couple minutes, I guess. And at some point, they're going to stop the air portion, and then they're going to have to purge the air out of the pipes, which is very noisy. I will mute it. not be deafened by that. Turn it way down. Okay. So you see that's probably very pleasant to listen to there. So they're just purging the air out of that, and then they're going to start pushing water through once they have that primed. There we go. All right. So now they're going to start pushing the water through. There's still a lot of air trapped in the grains themselves, so you'll see bubbles coming out, and that's part of what's helping kick all the particles out. It's just the fact that it's been jostled around so much.
This is how they make root beer.
So you'll see what they're talking about in a moment. Somebody said this is how they make root beer. So the water is going to raise up to these troughs. And there's your delicious particle view. So this would be just a collection of all the particles that have been filtered out of the water in the past cycle time, maybe 24 hours, 36 hours, something. And it's pretty typical to see these with these trough systems. When you're loading water to be treated, you'd use this central trough and flow into it, and then it would disperse into these troughs and go onto the beds from there, and then the backwash, the whole process kind of reverses and draining water out of that centerpiece, as you see. So you can see why we're going to send that water to a wastewater stream, and it's so full of particles that it's probably going to be pretty easy to do some flocculation and sedimentation on that as the first steps. A lot of times this granular filtration happens after the sedimentation, right? Occasionally you'll have it in place of sedimentation altogether if there's not too many particles. And so essentially what you see here is that
one simple hearing hack.
Okay, great. What you see in those scenarios is that now that the particles have met each other inside the pores of the grains, you'll have had more flocculation type of stuff happening, and you just have such a high concentration of particles that from there it becomes pretty easy to do sedimentation again. But really that would be really in the wastewater treatment. You might have a small wastewater treatment step to deal with this type of waste coming from the drinking water system, but a lot of times they would send it straight to an actual wastewater treatment plant. All right, so I'm going to get some of the lights back on so you don't fall asleep. All right, and I think in the past I've shown some more backwash videos. You can find some that it's pretty neat. Sometimes you can see the different color of particles. Like some will be pretty orange instead of the brown. And then if you watch a backwash video up until the point where it's clearing up, you can kind of see that it almost looks like cloudy wisps of particles that are escaping, but it's just becoming more and more clear, and it kind of makes a neat look. Okay, so from there, next step will be to calculate some filtration rates, and I've got some more slides for that. All right, so we talked about this, that determination of the backwash frequency, and from there, that's going to tell us something about how many filters do we need to actually produce some set amount of water. So if we have to meet the demand of some community, let's say they need 5 million gallons per day of drinking water, then we need to be having filters that can produce more than that at any given time, because we have to consume some of that, right? Because some of the filters will be down periodically. So we have to have a net that is higher. Like if all filters were active at that same time, that's going to be a higher amount than we actually need, because we have to account for the water that we're going to consume. So on the whole, we could say that we have some flow rate demanded by the entire plant. That would be our Q in this case. So this would be our Q for total demand. And we could take a look at how much we need in terms of what we will call a flux. I heard of some of you mentioning that from another class you're dealing with flux, right? So flux in the sense of water across our filter here is really just a flow rate divided by the area across which we're flowing. So that's going to be our definition of flux. And so when we consider the amount of water a particular filter can give us, that's going to be very important to relate to the amount of water we need across the entire plant. And I'm gonna clarify here. I think I was a little ahead of myself saying Q total here, and I'm gonna just distinguish this very clearly for you on the side. So I have this note down here for Q plant versus Q filter, and I was a little ahead of myself here. So the Q plant, or we might say that's the Q total, that would be the total output required. And so when I say that's not equal to the Q from one filter, we have to make sure that we have these kind of separated in our minds. So we could say that the Q, we could say that's Q total, Q plant, whatever. The Q total would be equal to the number of filters times the Q for the Q net for one filter, right? That's kind of obvious, right? If we have 10 filters and we need, some amount of flow, then that flow is coming from whatever the 10 filters produce in a net manner. There's another aspect here where we might have the Q coming from a filter during filtration, which is not going to be equal to the net amount coming from a filter. So the Q, a flow rate for one filter, and I'll say during filtration or during operation, is not equal to the Q of the one filter on a net scale, right? That's all I'm saying here is that when we're producing water, or during the filtration step, we're making, we have a flow rate that's higher than when we account for all the water we wasted during backwash. All I'm saying is there's a difference there, and that's what we're going to get into here. All right, so a typical production rate. I say production rate, we're talking about that during operation. So during operation, we will typically produce something like anywhere from 5 to 25 liters per square meter per second. So this is a flow rate divided by area, right? So that's our flux. that would be equivalent to 2 to 10 gallons per minute per square foot. Okay, so then we have another term, we'll say loading rate. This is synonymous with production rate. So at what rate are we loading water onto the filter during filtration? That loading rate or production rate as it's going through, we're going to define that as VA, lowercase v subscript a. And so when we consider that, we could define that as the volume of water that we are producing divided by the area of the filter per time, right? So we could get some, it's a strange noise. Maybe we produce 10 cubic meters in an hour or something. You know, that would be the volume, the 10 cubic meters, the time would be an hour, and maybe our filter is 10 by 10 meters, so it's 100 square meters. So that would be a way to calculate our loading rate there. Another way to say that is the Q during filtration of that one filter per area. So this whole process is really all about distinguishing between the active production and the net production. So the active flow rate during filtration compared to the net flow rate we'll get. Got some cool sound effects today. That was coming from this? What? I don't have... Was that my speakers? No. Okay. It stopped as soon as I hit mute, and then it started when I unmuted. Getting really confused there. But right now I'm muted, so that's not us. Okay. All right. So it's gonna be a little bit like beating a dead horse here, but I'm doing it on purpose because I know this does get confused and does sometimes become a problem. I'm just gonna double check that I just don't have any sound on here. I think it's some sort of construction outside. But there we go, we're muted. Ceiling speakers are muted. All right. So let's come back to our little drawing about the actual pieces of our filtration cycle. So a given cycle here, we will have that rinsing or ripening. We'll have the filtration. This is the bulk of the time. We might have an air purge. We're not using any water. We're also not producing any water during that time. And a backwash. We are not producing and we are actively removing water that we already produced during backwash. Okay, so we'll define our filter efficiency as a water basis. We're also going to have a similar related term, the effective loading rate, but we'll come back to that in a minute. The filter efficiency, this is on a water basis. What percent of the water is the filter giving us as usable water? So a highly efficient filter doesn't need to be backwashed very often, or maybe you can backwash it with just a little bit of water. It turns out when you have granular media, they're relatively similar, right? You're not going to have some super high-tech sand particles. I mean, I guess there's probably a little bit of research on how to optimize them or whatever, but there's only so much you can do with sand grains to make them high-tech, right? So these are going to be pretty typical, and we could just define it as this here, as the volume that we filtered minus the volume that we consumed for backwash and rinsing, divided by that total volume that we gave to it in the first place that we filtered. So this will be always less than 1 because it's a fraction, and we will have backwash something and rinse something, right? So we know that's going to be some fraction less than 1, and that's going to be pretty straightforward, it will often be 95% or so. If we want to convert it to a percent, we can multiply by 100%. So maybe we have 0.95 as our filter efficiency. That would be 95% efficient on a water basis, right? Okay, so then the question might become, well, how do we find the amount of volume that we actually used or produced? And that's going to be kind of on the basis of our loading rates or our backflushing rates and the area of a given filter. So rather than just telling you, oh, we filtered 300 cubic meters of water, really you'll be dealing with something like, oh, our loading rate during filtration was 10 liters per second, or whatever, per square meter. And then you find a volume by calculating. So a very simple equation will be just to take a look at what we were saying a few minutes ago, where we define that loading rate as the flow rate divided by the area. We could also look at area of that particular filter. We could also define that as the volume over time times the area, right? And so we're just going to rearrange this equation to say, to solve for volume, uppercase V. I'm going to try to keep that uppercase and lowercase clear for you. This would be equal to that loading rate times time times the area. So this should be very intuitive, right? Almost stupidly so that, it's pretty obvious that you can get here. And again, a good reason to pay good attention to your units. So the volume filtered then would be the area of the filter times the loading rate times the time during filtration. The volume that we used for rinse would be the area of the filter times the loading rate times the time for the rinsing stage. One thing you'll notice is for the filtration and for the rinsing, we always load those at the same rate, because we rinse at the same rate that we will filter. Because really we're just starting the filtration, we just have to discard some of that water that's going to come out dirty. So rinsing always uses the same loading rate, VA. For the backwashing, sometimes our backwashing might use a different rate. We can sometimes push water more quickly through, give it a little more turbulence, just flush it out real quick, and be done with it, right? So assuming our system can handle that, and assuming we're not going to lose any of our granular media, you can, if you ever want to come over to my lab, we can do backwashing. You can see it's very possible to push the granular media back out of the inlet when we do a backwash. And so you have to be careful with the flow rates. So there's some limitation there, but typically this VB, the loading rate for backwashing, or let's say backwashing rate, typically will be anywhere between 1 to 2 times the VA. If you don't see any information anywhere about it, and it's not something you're solving for, maybe you could just write out your assumption that it's going to be the same. But usually there'll be some piece of information in the problem itself to describe that. Okay, so during the rinsing, we would use the loading rate. During filtration, we'd use the loading rate. And during the backwash, we'd use the backwashing rate. Okay, so that's how we would solve for our volumes. And we just then need to know, well, how much time was dedicated to the backwash? How much time was dedicated to the rinse? We could also back calculate potentially and say, well, we know our filter efficiency, we're given some filter efficiency, we could potentially solve for, if we knew that there was no air purge and there was VB was VA, we could probably solve for how much time was dedicated towards the combination of filtration, of rinsing and backwashing. All right, does this make sense? Okay, so filter efficiency, pretty straightforward. On a water basis, what's our efficiency? On a in terms of how much water are we effectively getting, this is going to bring us closer to understanding how much water one filter can produce for us that we can rely on. And when I say rely on, I mean if we need a plant that does 10 MGD and we have 10 filters, each one of those has to reliably, in the net, provide 1 MGD, right? So if they're operating on a 24-hour cycle, each one of those has to produce more than 1 million gallons so that you can account for the backwash used. So on the net scale, trying to meet the demands of the plant as a whole, we have to we need to calculate that. So we're going to take or to find an effective loading rate, REF. So our book defines it this way: lowercase r subscript EF. So this REF is going to be that net loading rate, or the effective loading rate. This is going to be essentially the same thing as VA, the loading rate, except we're going to account for the inefficiencies due to the time taken for the backwash, the rinse, the air purge, and the water consumed there. One thing I forgot to mention a moment ago: these loading rates, VA and REF, these look a lot like a velocity. This is essentially meters per second, right? And what I'm talking about is the water is traveling through some plane at some rate, right? And so it comes to this, meters per second or meters per minute or whatever, because if we take a look at Q over area, this is a volume per time per area. And so if you divide volume by area, you get just one dimension, right? And so that becomes, if time is seconds and volume is in meters, that would become a velocity, meters per second. Okay, you could also write it, if you wanted to, instead of meters per second, you could do something like cubic meters per square meter per second, right? So this is, again, that concept of flux. It's kind of a velocity through a plane, or it is a flow through an area, right? So keep that in mind. REF is working exactly the same way. The loading rate effective is that way, and our loading rate during filtration is that way, and that backwashing rate is also that way. So all those are kind of the same type of term. Okay, so this effective loading rate then, we're going to define this as the amount we produced per area minus the amount we used for backwashing per area minus the amount we used for rinsing per area. These are the volumes per area. And then divide that by the entire cycle time. The entire cycle time, including any time spent to do air purge. So this would be T for rinsing, T for filtration, T for the air, and T for the backwash. So we could call all of that in total TC for T for the cycle. So the total cycle time would include all of that. And one thing we'll notice here is this equation starts to look pretty similar to our filtration efficiency equation, because it's kind of like, oh, the volume here minus these volumes divided by the total. So you would think to yourself, well, can we convert from the filter efficiency to the net loading rate? And you almost can, except that the filter efficiency has no bearing on the amount of time you spent doing air purge. So because we might have an air purge step, they're not actually a direct correlation. I'm going to write this and then erase it just to show you what I'm talking about. It almost works, okay? But I don't want you thinking this way. So don't make this mistake on exams or problems. But it's almost as if you could take the loading rate times that filter efficiency to get our REF. It's going to be close, but it's actually not the case because of the air purge, right? So if you wanted to check and see if you're in the ballpark, maybe that makes sense to do. And you'll see that if a efficiency is something like 0.9 or something, our effective loading rate that we get after averaging out all the wastes should be lower than the VA. We do know that. So it'll get you to the ballpark if you needed to check something. But I'm gonna erase this because I don't actually want you thinking about it in those terms. It'll just be better to kind of keep those ideas a little bit separate. All right, and really that's because of this air purge step. It might actually work out to be true if you didn't have that. So this is the term then. We can simplify it and say we have the volume filtered minus volume backwashed minus volume rinsed, and all that divided by the area of a filter times the cycle time there. Again, we can define the volume of any one of these as the area times the loading rate times that time. All right. So you'll have these equations on the exam, that one and the filter efficiency. So it'll be more a matter of just understanding the system as a whole. Where do these pieces come from? And this is not an equation I will give you. So this is something I'm asking you to put into your memory or intuition, that you can do a units analysis to say, all right, we've got this flow through an area, that flux, and figure out how to calculate the volume here as needed. Okay, so that might be one aspect to practice and get a handle on. Okay, does that make sense? Feeling all right about that? Okay, so let's give it some practice then. So we have this problem from our book. It says a conventional water treatment plant treats 2.4 cubic meters per second of river water. The filters in the plant are 8 by 8 meters in surface area, and they operate on the following schedule. The filter is cleaned once in each 24-hour period. The backwash rate is 10 liters per square meter per second for a period of 8 minutes. And it takes an additional 8 minutes to drain the filter and break up the media with air injection. And so you'll see here, one thing that they note is, they give us 8 minutes of air plus drainage time. That's kind of practical, right? If you're going to do the air purge, you probably have to drain it first. And that takes a couple minutes. So really what it's doing is lumping in the amount of time where we're not actually consuming any water into this step. This is the air purge step. Okay, so 8 minutes of backwash, 8 minutes to air purge it. Of the total filter cycle time of 24 hours, 15 minutes is used for rinsing the filter after backwashing. And during production, water is applied to the filter at a rate of 5.5 liters per square meter per second. So part A says, what is the filter efficiency? And then part B asks, what is the minimum number of filters required by the plant? Okay, I'll write up our equations here. All right, so I'm going to give you a little while to work on that. Can work together if you'd like. time. Almost done. Was that a yes, more time? All right. So I have a Kahoot for this one. So we'll do that, and then we'll go through some of the solutions real quick. So join with your 8-9 number. No dashes or anything, just the numbers. I see an 8-0 number, that's just probably a mistake, so try to correct that if you can. All right, everybody in? Anybody need a moment? All right. So based on your answers that you calculated, first thing I'm going to ask for the volume. So what was the volume filtered that you found? Okay, so looks like we had some slight difference in the calculations there. We'll take a look at that, but most of you were getting something on that order. How about the filter efficiency? Okay, most of you had that right. Again, a few that were a little bit off. All right, so what was your answer for the minimum number of filters? Okay, so a few of you may have thought to yourself, well, I got 7 point something and I'm going to round to the nearest, but you really can't round down ever with a minimum number like that. In order to supply that much water, you have to go up. You have to round up, if anything, right? If it required anything above exactly 7. So that may have been one of the issues there. Okay, so let's thank you for that. And as always, don't sweat it much if you did felt like you got all those wrong. That's really not going to harm you much in the scheme of things. So you'll have the majority of the credit for just simply participating, and that's what I'm trying to encourage is the participation there. Okay, that's interesting. How about we power it on? I guess the system also wanted a break. Okay. So filter efficiency. We had, well, first of all, we need to calculate the volumes, right? So the volumes for each of them, each of the filter, the rinsed, and the backwash. We said these are going to be the area of the filter times the loading rate times the time involved. Now, we have, for the backwash, we were given a specific backwash loading rate. So whereas the volume filtered is going to be, the 8x8 should be 64 square meters times the loading rate, which was 5.5 liters per square meter per second. The volume for the backwash would have been 64 square meters times this 10 liters per square meter per second. Rinsing would also be pretty straightforward, like that. Okay, so then when we take a look and we are trying to sort out and find the values for each of these, we do need to account for the fact that we've got liters instead of cubic meters for the volume. And so we could recall that there's 1,000 liters in 1 cubic meter of water, and that would allow us to convert, for example, to say 0.05 cubic meters per square meters per second is our loading rate, basically dividing by 1,000, the 5.5, and I did that wrong, sorry. That 5.5 divided by 1,000, 0.55. And would do the same thing with the backwashing rate. So we need to convert that, get everything to meters. And then we also will take a look at the time for everything. The time for the total cycle was 24 hours. Time for the backwashing was 8 minutes. And so we're going to have to convert between hours, minutes, and seconds when we put all the pieces together to make sure we're in the correct units. Time for the rinsing, I think, was what, 15 minutes? 15 minutes or a quarter of an hour. And the time for the air was 8 minutes. Okay, so then with that, we can do some calculations. I have this completed in Excel, so what I will show you here when we can convert, find each of the times in seconds, and then for the volumes, we can look here. So for the volume filtered, this should be equal to, that was 29,700 cubic meters. We can find that by simply multiplying our time for filtration. And that's something I didn't mention, right? The time for filtration has to be, that's another thing we need to solve for. That time of filtration is going to be equal to cycle time minus the time for air, basically anything else, right? Time for the air, time for the backwash, and time for the rinse. So that'll be 24 hours minus 31 minutes, right? So 23 hours, 29 minutes, I think. Okay, so with that, then we get this 29,000 value. 29,760 basically. Okay, the volume rinsed we got was 317 cubic meters, approximately. And the volume backwashed would be not too far from that, 307 cubic meters. Okay, so then we can put that together from there, solve for our filter efficiency, and that's going to give us a value of 0.979. Okay, good, got some more room. So then for part B, we want to know what's the minimum number of filters to meet the demands here. Well, we know we have to have a total flow rate as 2.4 cubic meters per second of water. So we have to essentially calculate this Q total is going to be the effective flow coming from one filter times the number of filters, as one way we could look at that. So we could write it as Q effective for one times, that's one filter, times the number of filters. And we could also kind of rewrite this. If we wanted to, we could do like the total area of filters required. So you could solve it in terms of, well, what's the total area of filters we need? Divide that by the 64 square meters of one area. So there's a couple ways you can approach this. And I'm going to say that let's take a look at the effective flow rate for one. This would be the number times this effective. We'll take the REF, so the effective loading rate times the area of one filter. So the effective loading rate, that's the flow per area, multiplied by the area, should give us the effective flow of a filter. Okay, so that's the way I'm going to conceive of this and say that, well, we know the Q total, so we can rewrite this as 2.4 cubic meters per second as the requirement, equals the number of filters that we're interested in times the R effective that we can calculate times 64 square meters for each filter. And we could, if you want to be a little more explicit with the units here, we could say per one filter, and the number of filters times per filter will give us just a number. So you could even do the units like that if you want. Okay, so then really what we need is this R effective, and we said that's going to be the volume filtered minus the volume backwashed minus the volume rinsed, divided by area of the filter times the total cycle. And we've already solved for each of those pieces and over 24 hours. And so this should be just simply a matter of going back to our calculations to say, okay, well, what have we calculated? And from there, we can find a value, a number coming out to be 7.11, or I guess 7.12 there, for our effective loading rate. And this is going to be something like cubic meters per square meter per second. Actually, I probably have the, yeah. And if we, let's see, did I do that? Did I put the right units? I'm sorry, I jumped ahead of myself. I wrote the wrong number. So 0.0053 there. Okay, I had to stop and double check myself because I was thinking this should be just a little bit below the VA, right? So the VA, the loading rate was 0.0055 once we put it in meters and seconds, or cubic meters per square meter per second. And so this number we can double check in our mind that it should be a little less than our actual loading rate. The effective should always be a little lower than the actual. And so when we get this number, then we can solve this equation to say the number of them was 7.12. And like we said earlier, we have to round up to get a whole number. Because 7 filters will not treat enough water for that plant. And if we do round up, one of the nice things there is that gives us a little extra treatment capacity. So we can actually have them running at slightly lower loading rates, or we have a little more flexibility to add capacity if we need it. Yeah.
Could you do Q total is equal to efficiency times the overall flow rate times number of filters, or is that the wrong way of thinking?
When you add the efficiency in there, you're dealing the water efficiency is not quite giving you the same thing we're looking for. So this problem kind of leads you astray by asking what the filter efficiency is in a sense. It's almost there. And maybe given the rounding that's going to happen, maybe it's okay. I haven't checked it, but like I said earlier, the air purge there is not caught by the efficiency. So it's probably close. All right, so that's it. And we'll see you guys on Thursday.